doing the best they can with what they've got. And that's where we all are. Every one of us is in that same boat. So have compassion for those people who are struggling. Words, sometimes it sounds like we're saying opposite things, and we're not. Like some people will say, you've probably heard the phrase, you can't love anybody else or anything else if you don't love yourself. You've probably heard that. And then somebody else will say, oh, loving yourself, you need to stop that. That's ego. You don't want to focus on yourself. And now you're thinking, well, what's going on here? Those are contradictory. They're not really contradictory. It's just words and the way we interpret them. When you say love yourself, you're not talking about thinking, oh, I'm greatest. I'm wonderful. I love myself. I'm so great. That's not what's meant by that. What's meant by love yourself is get rid of the problems that are dragging you down. It's not a matter of being thrilled with yourself. It's a matter of not having the blocks, not having the things that inhibit you, not having the things that are dragging you down. It's cutting loose of that sort of stuff. That's what's meant by loving yourself. It's basically growing up. So there's no real difference there. Loving yourself doesn't mean blow up your ego. It means get rid of your problems, get rid of the weights. So words, when I say things that sound real, kind of like fingernails going down the blackboard to you, it might just be words that we're not understanding each other. So ask those questions. We'll talk a little bit about models. What I'm going to present to you is a model of reality. Okay? And it's very important that you get this idea that the model of reality is not reality. Okay? There's a difference between the model of reality and reality. There's a difference between the map and the territory. Okay? And this is an important differentiation that's sometimes hard for people to get. The experience you have of a larger reality is a real experience, okay? That's your experience. But now for you to take that experience and put that experience into words so that first it seems rational to you, and secondly, so you can explain it to somebody else, that process of translating turns it into a model. What's real is the experience. How you express that experience is just a model, metaphor of what you experienced. Our language does not allow us to talk directly about non-physical things. Our language developed in a physical reality to express what happens in physical realities. So we can have a real experience, but then remember that when you take those experiences and turn them into a model, it's just a model. It's not reality. Now, there's a lot of different models, and it's not like there's only one model that's right and the rest are wrong. Different models, just approach it, describe it differently. You can have different metaphors for the same thing. So be aware that what I'm telling you is a model of reality, and be aware of what you believe is reality and is also a model of reality. So what's in your mind's a model, what's in my mind's a model, because we can't actually share experiences. We share words and thoughts and concepts and metaphors and symbols is what we share. Okay, so keep that in mind. That's important. Now the last thing that's kind of the getting us oriented properly is what this is about is spirituality, about love, about growing up, about decreasing your entropy, and we'll get to that a little later. It's not about traveling around in the non-physical. Okay. Now, do you need to learn to get out of your body or travel around in the non-physical or heal or do any of these things that have to do with manipulating consciousness from the non-physical in order to grow up? No, you don't. All that's optional. It's not required. Okay, so we're going to talk about that a lot because that's what people are interested in. That's what they really want to know about. The non-physical is a very attractive flower. It brings a lot of interest and excitement and energy. But it's not the goal. The goal is love. The goal is to grow up. This is just another thing that you can do with your consciousness. We're going to talk a lot about it, but I don't want to leave the impression that if you don't go out of body, if you can't fly around in the non-physical, then you're just not getting anywhere, you know, that you're not evolving. That's not true. You can evolve your consciousness without ever experiencing the non-physical directly. It's not a requirement. It's just something else that you can do. All right, let's get started. I like to start with Einstein. It's like starting at the top. Einstein probably was one of the, without a doubt, the greatest original mind that we spawned in probably all of our lifetimes, and maybe longer. So here's what Albert Einstein's conclusions were after 20-some years of studying a model of reality. He wanted to write a toe. He wanted to come up with a toe that combined with one understanding the two major parts of physics of the day, and that was quantum mechanics and relativity. And where those two boundaried together, there was discontinuity. One did not lead to the other. They were like two separate things. You couldn't go from one and derive the other. They were just different things, and they clashed some places. So he wanted to bridge that gap, and that's what's called a toe. It was the first scientific toe, was one done by Albert. And after 20-some years, he failed. He could not bridge the gap, but he got real close and came to some very interesting conclusions. These are some of the conclusions. Space does not have an independent existence. That's a pretty big thing for a physicist to say, right? Space does not have an independent existence. It's in the first bullet. Reality is an illusion. Okay? He said, hence it's clear that the space of physics is not, in the last analysis, anything given in nature or independent of human thought. It's a function of our conceptual scheme. Okay? So he's saying that, space, which is the most fundamental thing that we have, that's kind of, we live in a 3D reality. That defines space. That's the most fundamental characteristic of our reality is space. And here's Einstein comes at the end of his career saying it's an illusion. It's nothing independent of human thought. Okay, next. Okay, David Bohm was a physicist also. He worked with Einstein. He also worked on unified field theory. And to meet the challenge before us, our notions of cosmology and the general nature of reality must have room in them to permit a consistent account of consciousness and vice versa. In other words, he realized that this toe, this theory of everything, was going to have to deal with consciousness. They didn't want to go there. They just wanted to do relativity and quantum mechanics. That wasn't what they wanted to do, but they realized that it was going to have to include consciousness. Consciousness and the physical reality had to be worked together. Okay, they had to be understood as a whole. It says, one has to find a possibility to avoid the continuum together with space and time altogether. This was Einstein now, a letter back to Bohm. He says, but I have not the slightest idea of what kind of elementary concepts could be used in such a theory. So that was the wall they hit. It had to do with consciousness. Time and space being continuous was a problem, and they didn't have a clue what the next step was. Okay, next slide. Okay, then we have Wigner. Wigner is a Nobel Prize winner, and he was also part of the team that generated quantum mechanics. A very original mind. Quote, it will remain remarkable that in whatever way our future concepts may develop, that the very study of the external world, he was talking about development of quantum mechanics basically, would lead to the scientific conclusion that the content of the consciousness is the ultimate universal reality. That doesn't sound like physicists speak, does it? But these are the best physicists, probably, like I say, in the last 200 years or so, maybe forever. These are people with minds that were able to get out of the box and go beyond what most physicists could do. And after many years, these are the comments we have. Well, they said that time and space was not continuous. They realized they couldn't, that didn't solve the problem. Physical reality is an illusion, does not exist independently. It's a mental construct. Okay. Consciousness is somehow the root of reality. The relationship between physical reality and consciousness is fundamental but unknown. Okay. They knew that the assumptions that they had to work with, the fundamental way that physicists looked at reality was wrong, but they didn't know what to do about it. Okay, why did they get stuck? They were only looking for continuous solutions. Fact is that reality, space, and time is digital, comes in discrete units. Okay, now everything in our reality, physicists will agree, everything in our reality is digital. This lectern is made up of particles, individual particles with nuclei and electrons and huge spaces between them. It's mostly empty space with little particles going around. So that's discrete. It comes in discrete chunks. It's not really continuous. It just feels that way here. We think of it as being continuous. And that's been true of everything. When it gets down to biology, it's independent things with space around them. Cells, and then you look at a cell and you go inside that and they're still smaller and smaller pieces. And physics gets it down to what they call subatomic particles, particles that are smaller than electrons and neutrons, the things that make those things up. These elementary particles then are thought to be the most elementary thing there is, but as the years go by, all of our elementary particles keep being broken into more elementary particles. It seems to be the way that we go. So everything in our reality is known to be digital in the sense that it's discrete. It's not a continuous thing. The only two things that physicists don't put in that category are time and space. Well, the early quantum mechanics gurus calculated a distance in which space became granular. It's called the Planck distance. But that was just theory. They didn't really know what to do with that. It's so small that you don't notice it as the thing. Same with time. Time is actually, comes in discrete units. So we have, it's like a simulation. Delta T, at a time, clicks on, and time seems to be continuous if that delta T is small enough. If it's so small you don't notice it, it seems like it's not sequential. It's just a continuous thing. So that was one problem. They expected that the physical reality was fundamental and not derivative. Big mistake. They were trying to derive, the fundamentals of reality from physical reality. Well, physical reality is not fundamental. It's a derivative. So that was a problem. Okay, consciousness is the larger reality, and the physical reality is a virtual reality. They were looking for an objective solution. Consciousness, the only thing that is fundamental, is not objective. It's subjective. Okay. As it turns out, even the physical world is not objective. It's all subjective. They were looking for an objective solution. They could not find one. So that's the wall that they hit. Consciousness is personal. Right? I mean, there is such thing as group consciousness, but consciousness, that's just a vector sum of all the individual consciousness. Consciousness is personal, subjective. Okay, next. Okay, now we're going to look at, Einstein. That was back in like the 1920s, 1930s, 1940s. We're talking about the early 1900s. So what about now? Where is physics today? Well, quantum mechanics is the main thing that tells physicists that reality isn't the way they thought it would be. They have problems. There's a thing called the wave-particle duality, which comes to a measurement problem. We're going to talk about that in a little bit. That was the thing that basically created quantum mechanics. I'll get a little more detail. What it amounts to is that particles matter. Matter's the other thing that's fundamental. Space and matter. I mean, that's our reality. That's our physical reality here. And it turns out that space is an illusion, according to Einstein, and then it turned out that matter is nothing but probability distribution. There's nothing hard and solid there. That was the fundamental conclusion of quantum mechanics. When physicists describe what small particles do, and the small particles are what build up all the big stuff, right? It's all built out of these small particles, so they're at the root. And these small particles don't actually exist as physical things until you measure them. They exist as probability distributions. And the whole science of quantum mechanics is dealing with probability distributions. We'll see a little bit more of that. So here we have, quantum mechanics. It says matter really is just a probability distribution. All the particles that make up this stuff we see are just probability distributions, and that space is an illusion. Okay, there are a lot of theories about why particles ought to be probability distributions, and actually physics has no idea why particles ought to be probability distributions. That's a great mystery. Unfortunately, these books, My Big Toe, we derive that. We derive quantum mechanics. So a logical derivation of why particles have to be probability distributions. So a good toe needs to describe not only the physical world, like Einstein wanted to do, but it has to also describe the non-physical. It has to describe the subjective, mind as well as matter, the paranormal as well as the normal. It has to describe all of those things. So they have some ideas that consciousness causes collapse. That's one of the theories, and that's because when a consciousness makes a measurement, suddenly the probability distribution collapses into a particle. So that was one. There's another one called many worlds, and that is every state that these elementary particles can be in defines another reality frame. Now this is standard physics. This is not even fringe. Many worlds is a standard physics idea, and then the correlate to that is many minds, and that is that these worlds exist in mind. So these are, they got some threads of truth in them. These are getting kind of pointing close to the truth here, and this is where physics is today. Okay, next one. All right, here's that double slit experiment, and I want to go through this in a little detail because it's kind of at the basis of where science is today as far as reality goes. Okay, here's a photon, and this that's a particle of light, if you will. It's a little packet of energy. It's a particle of light. It always travels at the speed of light. It has mass while it's traveling. If you stop it, it doesn't have any mass, kind of a magical particle. But the same thing works. The same thing I'm going to go through here works with an electron, which is a massy particle, as it does with a photon. So it's not about photons being weird particles. It's you take a photon, one single photon, and you shoot it at this screen. This is basically a wall with two holes in it. It's called the double slit experiment. What they found out is that if you do that, you get this wave pattern on a screen in the back. That's where they take the measurement. Okay, now, how do you get a wave pattern? What you would expect is that the particle either goes through this hole and makes a spot right behind that hole, or it goes through this hole and makes a little spot of light right behind that hole. Photon, a particle of light. But that's not what happened. What they got was this wave pattern. Now, what a wave pattern is, as you can see from these lines I have here, is that if you consider something going through each of these two slits, you notice these two lines are the distance between each slit and that point. If those two lines are exactly some number of wavelengths apart, then the wave hump and the wave hump, from both of them will happen to get there at the same time because they're one wavelength apart. They're just shifted in a wavelength, but the humps will be on top of each other. It's called superposition, and that's why you get a spot of light. And in here, between all these pieces that are between spots of light, you get a hump of one wave with a dip of the other wave, and they cancel each other out, and you get nothing. So it's black there. Okay, and the problem was, of course, that how do you get a wave pattern from a particle that should go through one hole or the other? That was where, this was the origins now of quantum mechanics. So they said, well, that's a big mystery. Let's measure where this, which one of these slits that it goes through. So now they put a little measurement device on each one of these slits, and they put a photon to it. And if they measured it going through here, guess what? They got one spot of light right behind it. And if they measured it going through here, they got one spot of light behind it. And then if they didn't measure it, they got this. Okay, so that was what's called duality. How can light be a particle and a wave all at the same time? That was the problem. Okay, next slide. Here's the solution. This was the invention of quantum mechanics. Schrodinger, Heisenberg, and some of the other very good physicists at that time said, well, look, we can get the right answer if we assume that this photon isn't really a particle, but it's this probability distribution. Here's probability, and there's distance, and it goes up, so we think it's mostly here, but it could be out here, and it could be out there, and that probability distribution actually gets asymptotic in both directions. So this is some probability distribution now, and it could be anywhere. It's not really a particle, and when the probability, there's some certain amount of probability it'll be through here, and a certain amount of probability it'll go through here, and then those two probabilities combine as waves, and that's why we get a wave pattern. Okay, so that was their explanation. Because how can a particle go through both holes at the same time and interfere with itself was the problem. Well, it's only probability. Now, they had no idea why that ought to be right. It seemed like a silly idea to them, but when they did the calculations, they got the right answers. They could predict what was going to happen by using this math formalism. It drove graduate students in physics crazy for many decades. They'd be saying, well, what's waving? Well, nothing's waving. It's just a mathematical formalism that we use to get the right answer. There was no explanation for it. Okay, the next one. Okay, here's what's really going on. We've already kind of explained this, there's probability distribution. Here's the measurement screen. You're taking your measurement here. Until you get to the screen, there is no measurement. If there's no measurement, the particles exist only in probability until they're measured. Once they're measured, what we're asking here is, what is the probability of light being at any point in the screen? Well, what's the probability of it being, here? Well, if that's an integral difference of wavelengths there, then the probability is higher. And here, and it's zero in these spots. Once you do the measurement, here's the present. So this is the present where you do the measurement. You always do measurements in the present. Now here's the present. Now you're doing a measurement, and here is where you force the particle to come into reality. The physicists say that the wave function, which is a probability wave, the wave function collapses to a particle. So the probability wave function collapses to a physical particle. Well, it collapses to a physical particle right there because that's where you're making the measurement. And once it's a physical particle, it can only do what a physical particle can do, which is travel in a straight line. Up here, you don't make the measurement until this point. So it acts like a probability until you get to that point. So it matters where you make the measurement. And you're thinking, well, look, it's those detectors. Those detectors have something to do with it. Well, so then they said, well, let's turn the detectors off. So they left the same setup, and they just turned the detectors off, and they got this again. So then they said, well, it's still those detectors. In fact, we turned them on and off. There's fields, there's electromagnetic stuff going on, and we're interfering with things because of those detectors being on or off. So they left the detectors on. They turned them back on again, and what they turned off was the data line that the detectors were outputting. In other words, the detectors were there. They were still detecting or doing whatever they do. They were completely turned on and energized, but they have an output someplace. They draw a graph, they make a blip on an oscilloscope. There's some output where that data is collected from what the detector detects. Well, that's what they turned off. They just turned the oscilloscope off, or the printer, or whatever the final thing was, and you get this again. Okay? So that was the big mystery. So it's not the measurement devices. It's not the fact that you have these things here. It's basically if you take a measurement here, then you get these two spots behind either slit. If you don't take a measurement there, you get this. So that's why the first idea of quantum mechanics was consciousness is creating reality. That's kind of where they got this idea from, because it's somebody making a measurement. That seemed to be the key, whether or not you looked or didn't look. If you looked, you got this. If you didn't look, you got that. Well, what does looking have to do with it? That was a real big mystery. And it's still a pretty big mystery to science today. All right, next. All right, so now, today we have Edward Fredkin started a movement called digital physics, 1992. And there's probably hundreds of digital physicists now and all over the globe. It caught on reasonably well. It's still a bit on the fringe of physics, but then physics is kind of a fringe science anyway. Everybody knows us physicists are a little strange. So in '92, he gave a paper to a group of other physicists and mathematicians, and the basis of this paper said that the universe is computable, that time and space are digital, and our reality is a virtual reality computed. Computed reality. He said either reality is the computer itself, or it's implemented on the computer, like a simulation. It's essentially digital, and the fundamental nature is information. Okay, now that was a legitimate scientific paper given to scientists back in 1992. Fredkin wasn't just